Hi, I'm Jijoke Matthew. I'm here for my DAV research report presentation. My project was about the analysis of Plymouth air quality data of 2021. The overviews. First is aim, objectives, dataset, analysis and findings, recommendations and conclusions. First, the aim. The aim of the study was to analyze the dataset of Plymouth Center, which I have collected from the Air Quality England website, and it was to analyze the concentration of various pollutants present in Plymouth's air. The dataset has been taken from the air monitoring station of Plymouth Center. And from then we derived the research objectives. First, we performed descriptive statistics on the dataset. Then we performed the inferential statistics methods. Then created some machine learning techniques, applied some machine learning techniques on the dataset. And we performed some deep learning, created some deep learning models, and then we came to the recommendations and conclusions. First, going to the descriptive statistics. Before that, about the dataset. The dataset has been collected from the Air Quality England website and from the Plymouth Center Air Monitoring Station, and then goes to pre-processing. First, before going to the descriptive statistics, we have to clean the data. We have to pre-process the data for the model to accept it to get a better output. As part of data pre-processing, we have cleaned the, we have removed the unit columns from the Excel, means the CSV file, and we have handled the missing data with KNN imputation. And for that, we have performed with the help of the Python, we have performed the KNN imputation, and we have handled the missing, handle the missing data. And here, we have handled the missing data with the KNN imputation, and then we have described the data. Means we have explored the data with the help of the data frame in Python, pandas. With the help of the data frame, we have explored the data. Then we are going to descriptive statistics. Descriptive statistics means the understanding of the data. So we are summarizing the characteristics of the data with the measures of central tendency, measures of dispersion, and the measures of frequency. As in the scheme, we can see that we have taken the mean, standard variance, percentage, max, count, everything of the data attributes in our data set. And then we explore the means, and then we explore the histogram of the data, how the data is dispersed, means skewed. It's an skew stuff things in the descriptive statistics. Means we have understand the data much more with the descriptive statistics. And then going to inferential statistics, what we did is we performed the two-way t-test and to verify that the mean of PM 2.5 and particulate matter PM10 are not same. For that, we perform the two-way t-test, and we concluded that from the test output, we concluded that the means are not same. Then we perform the one-way ANOVA test, variance test, to determine whether the means of PM 2.5 for each month, PM 2.5 for each month throughout the year 2021 was same or not. We have to check whether we have to know the means of the PM 2. Particular matter PM 2.5 for each month is same or not. For that one, we have performed the ANOVA test, and we can see the output. The means the p-value is less than the alpha value, which is as default. We took the alpha value as 0.5 as a standard. It can vary from 0.1 to 0.5. 0.5 means as per our consideration, and we took it as 0.5, and we can see that the p-value is less than the alpha value. So we can reject the null hypothesis, which states that the null hypothesis says that the mean value for PM2 particular matter 2.5 for all the months are same. But we can see that the p-value is less, and we can directly reject the null hypothesis. And then we use the Pearson standard correlation method for identifying the linear association between the pollutants in the presence in the air, pollutants and other factors like wind, everything, wind speed, etc. So we perform the correlation matrix and we can see that there's a strong correlation between PM10 and PM2.5. It's 0.8. It's highly positively correlated. And we can see with wind direction, it's minus 0.1. It's negatively correlated. And we can see NO2 is also have some relation with the PM2.5. From the correlation matrix, we can understand how the data is the various features, various attributes, various pollutants are correlated with each other. Then we going to create some machine learning models. Especially we implemented multilinear regression model, random forest regression, and support vector regression. We have created 3 models for predicting the output of predicting the concentration of 2.5 based on the 2021 data. And our results are as below. We get the R-squared value little higher for the random forest regression, and the root mean square error was less for random forest regression compared to multilinear regression model and the support vector regression model, which means the random forest regression has a better accuracy in predicting our 2.5 concentration. So we can from here we can see that random forest regression has performed well slightly compared to other models. And then we deployed some deep learning methods, deep learning techniques for identifying whether we will get much output, much performance compared to the machine learning models. From here, we have used the gate recurrent unit and long short-term memory techniques. And here you can see the model loss. The model loss means how wrong it is getting predicted. Means that we have splitted the data set to training and testing model. The training to model means the machine is getting learned and the machine is applying, the model is getting applied to testing data, means the real world data, and we can see how it works, how it predicts with the real world data. And we can see for long-term short-term memory, LSTM, it started from high and coming, and at a certain point it comes parallel and near to, means that we have almost similar testing and training loss with long LSTM. And for gated recurrent unit GRU, what we can see is almost similar. At a certain point, the training data training loss has gone just above the testing data. Testing has gone just above the training data. And if it goes like it goes similar, we can see our model is good fit. The model loss means the penalty of the error. It is better. How less it is, that is better for that model is good fit. That's what this says. And we can see from the deep learning model, we can see the RMSE square for testing is low for LSTM. But comparing to machine learning and deep learning model, we can see that the random forest regression has better performance compared to the deep learning models for this particular data set. As because we only took 1 year of data set, means only we took 2021 data set, and means our data set cannot be, means we didn't perform any cluster classification or clustering, as data is a little bit more quantitative. So our recommendation for future works are, means add more data, means at least consider 5 years of data, and also consider other monitoring stations data, and perform create models, so apply more techniques of deep learning and machine learning models to, which means to validate the accuracy of the models. And that's our recommendation. And as the conclusion, as we saw earlier, we have the better performance for a random forest regression model, and obviously we can deploy the random forest regression model for this particular data set. Thank you. That's all.